All right, guys, as I mentioned, our course is about median voltage switchgear drawing and control systems, which involves reading and inspecting medium voltage switchgear diagrams. Very good. The first thing I always like to start with when I begin talking about any drawing in the world, whether it's median voltage switchgear, high voltage, extra high voltage, even if it's an AC distribution board, or even if I'm talking about it, the product, even if it was, or even if I was talking about it, a part like specific to factories, motor control centers, and so on. First, you need to make me understand, as you might say, the electrical network, and then you can get me into a specific part, telling me I want to get into, and so on. All right, here I'm telling you the first thing. What does it mean? Or what does it mean? Here I'm telling you the first thing. What does the electrical power network mean, or the electrical power grid mean? Look, guys, when I say electrical power network or electrical power grid, which is the electricity network, all right, so here I'm talking about the electricity network. I'm talking very simply, giving you a very simple definition. It is something called, it's like what you would call an interconnected network, meaning an interconnected network, which means an interlinked network. And what is this interlinked network? The interlinked network consists of a group of power lines, a group of power system lines interconnected with each other. So when you ask me what the electrical grid means, I'll tell you it's an interconnected network. So the grid, which is the electricity network, is an interconnected network. And what is this network? It consists of a group of power system lines. The power system lines. So what does a power system line mean? The power system line, quite simply, consists of three parts: generation, transmission, distribution. Generation, transmission, distribution, which are generation, then transmission, then what? Then distribution. It consists of three parts: generation, transmission, distribution, which are generation, then transmission, then what? Then distribution. All right, so how does the process work? To reach the grid, I first need to understand what a power system line is and then make them interconnected with each other to find the same entity, the grid. So we start first with the power system line. As I told you, the power system line consists of three parts: a part related to generation, a part related to transmission, and a part related to distribution. Very good, excellent. All right, regarding the part related to generation, the first thing you have is the generator, right? What is the generator? The generator, folks, is a rotating device or a rotating machine. Machines in general are divided into two types: either rotating machines, which are the rotating devices, or what we can call static machines, which are the stationary devices. The static machines are like transformers, and the rotating machines are like motors and generators, okay? The motor and the generator are somewhat the opposite of each other. What does that mean? It means the motor takes electrical energy, which is electrical power, and converts it into kinetic energy, which is mechanical power. Or the generator does the opposite. It takes kinetic energy, all right, and tries to, focus with me. It takes kinetic energy and converts it into electrical energy. Wrong, it's not a magician. It can't do something like that. There's no such thing as taking mechanical energy and converting it into electrical energy. So what is it then? It takes DC excitation or DC energy, meaning stable energy that comes from the DC direct current, all right? And by using kinetic energy, it tries to convert this energy into the form of AC power that we see. So the generator doesn't just spin and generate electricity. It needs a magnetic field to operate according to Faraday's law. Electromagnetic induction. If you have a conductor that turns a magnetic field, a potential difference is generated, and thus you can take electricity from it. It is the same idea. You have DC energy, and by using kinetic energy, you can convert DC energy into electrical AC energy. Turn the conversion of DC into what? Electrical AC energy. The important thing is that this generator is not something trivial. I bring it first. And it is responsible for generating the bulk power or the massive power that we will use. As I mentioned before, if I need this generator to generate electricity, there are two constraints or two challenges regarding this generator. What are these challenges? The first thing is to ask yourself a question. What is this generator supposed to generate electricity for? For what? I mean, you are talking about the load. What type of load do you have? That's number one. Number two, you might say to me, isn't this generator converting DC energy into AC energy using kinetic energy? I would say yes. then you would ask, where is the kinetic energy coming from? Or who is providing this kinetic energy source? So these are the two challenges I have. So the first challenge and the second challenge, all right, which one of them is more important now? Let me take them for you in order, starting with the second challenge, then the first one. What does that mean? It means that now for this generator to move, you have a turbine. This turbine is what moves the rotor of the generator, from which you will start transferring the DC from the field placed on the rotor to the stator. So how will this turbine rotate? If you're talking to me about renewable energy, then you're talking about burning fuel, for example, to heat water and use it to drive a steam turbine, or burning gas and using that gas directly to rotate your turbine. The important thing is that you need a specific source to generate energy. This energy can come from sources like waterfalls, gravitational energy, or wind energy. Is that correct, or am I mistaken? The important thing is that the source responsible for moving the generator determines the location of the generator. You can't just say you're operating within the city like this and expect to produce the large amounts of electricity you want. You need to be in remote areas, not surrounded by tall buildings, perhaps in the desert, so that the wind can reach them quickly and strongly. If you are using hydropower, you must be near waterfalls or dams, and you should have very large water reservoirs from which you can release water to start moving your turbines. If you remember steam turbines, which require steam or water vapor, you must be near a permanent water source. To start, you will first need to desalinate this source, like seawater, for example. You can't use it with its salt content. After desalination, you take this water and burn fuel to start generating your steam. So here, the first challenge you have is deciding where you will place the generator. Okay, you discovered that to place this generator, you might need to put it in a location far from where you live. All right, then you might ask about the type of load. There are various types of loads, so you might say, regardless of that, to generate power, do you prefer to generate it as low voltage, medium voltage, or high voltage? They said, let's see. If I generate low voltage, first of all, the power generated by the generator, which is a source of electricity, is measured in volt amperes because it represents apparent power. So what is this apparent power? It's volt ampere, as I'm telling you. Of course, regardless of the 3V line, I don't want you to focus on that part. Look at it more simply. The important thing in the end is that it's V times I, right? It equals a certain power. Now, this power is constant. Whether you generate 10 megawatts, 100 megawatts, or even 1 gigawatt, it's not my concern. You're generating something, right? This thing is voltage times current. If you generate low voltage, then the current must be high because, for example, you're generating 10. All right, great. So what is this 10? If the voltage is 2, then the current is 5. If the voltage is 1, then the current is 10. If the voltage is 10, then the current is 1. So what kind of relationship is this? It's an inverse relationship. Imagine you're telling me you'll generate low voltage. In this case, the current will be very high. So what's your problem, Rashad, with high current? It's a very simple problem. The first thing is that high current will affect the generator. It will reach the stator of the generator where the AC power is generated, which is your stationary component. Also, the rotor is the moving or rotating part, and the other is the static part. Now, for the stator to handle high currents, it needs a conductor with a large cross-sectional area, right? Great, a large cross-sectional area made of copper. So this definitely costs you when the size of the stator is huge. Handling maintenance and dealing with the generator becomes difficult during maintenance. Another thing, when the stator's conductors are large, the size of the stator will increase, and consequently, the size of the rotor must also increase. Therefore, to rotate the rotor, you need more power to turn it, right? This means you will consume more fuel, which from an economic point of view is not good. The other thing is, this generator is placed far from the location where you are present. So this current travels all this distance. And what do the losses equal? The square of the current times the resistance. And what about the resistance? You will see what it equals. We all know that resistance equals rho times the length of the conductor over the cross-sectional area of the conductor. Now imagine with me that this conductor is long. All right? In this case, you will find that the resistance is large. The square of the large or massive current that you generated, even if you increased its cross-section to try to reduce the resistance a bit, still results in a high value for the square of the current times the resistance, which causes significant losses. All right, is that all? No, the I2R also causes a voltage drop. So the quality of the voltage that reaches you is lower than the voltage you need. That's quite significant. So the cross-section of the conductor, whether on the stator, the cables, or the overhead line that goes from the generator to the load, all of this is massive, which results in a very high cost. The size of the stator is large, the size of the rotor becomes large, and therefore you need more power to turn the turbine. The I2R losses will be large, and the I2R voltage drop will be large as well. So someone might say, why worry? Just generate high voltage. And you say, okay. They tell you, high voltage means low current, and you agree. They say, this means the cross-sectional area of the conductor becomes smaller. You no longer need a large cross-sectional area to carry the currents, and therefore, the cross-sectional area of the cables or the trenches will also be small. All right, guys, so the cable's cross-sectional area has become smaller, which means your cost has decreased. I told him, okay, but now consider that the cross-sectional area is small, yes. But imagine the insulation inside being very precise, very large. So imagine every conductor in the insulator. You know, if you're making files and these files are carrying a voltage difference of, say, 380 kilovolts, usually each carrying a voltage difference of 220 volts will have very large insulation. Large insulation means the size of the insulator itself will be what? It will be huge. And consequently, the same idea applies to the size of the rotor, which will be large and also requires what? It also requires a lot of fuel to start burning it, to begin rotating your turbine. Is that the only problem? Of course not, engineer. When the generator is large with a voltage difference, with a very large voltage difference, a very large voltage difference makes it dangerous for the safety of the operator or the maintenance person to intervene. For example, to monitor things like temperature measurements, oil levels, or speed. You want to check the governor or whatever. You have a large number of sensors to detect any signals or anything present on the generator. You cannot enter in an area with 380 kilovolts. The controller and some of the control devices for the generator are close to the generator itself, and this also prevents you from entering. Another thing done during a physical inspection is to check the generator for any smoke or issues. I start to see if everything is okay. And in this case, none of this will happen due to the high voltage difference. I am not in a safe position, and therefore I cannot enter this field. So what is the solution? My best solution, or best choice, was to generate within the range of medium voltage, starting from 13.8 kilovolts up to 22 kilovolts. So what did I gain from medium voltage? Medium voltage stands in the middle. First, it is not as high as in the case of using low voltage, nor is it very low as in the case of using high voltage. This means I took advantage of being in the middle, where the current is somewhat moderate. My insulation is neither very low like low voltage, nor does it require very heavy insulation like in the case of high voltage. Therefore, the voltage will be moderate and the current will also be moderate. Consequently, the losses will be moderate and the voltage drop will be moderate or acceptable. The size of the generator, the insulators, everything will be reasonable. This is the main advantage of generating at a medium level.